Hello everyone, my name is Shinho Kim. In this video, I will introduce my research, the steering of directional thermal emission by using electrically tunable graphene metasurface. I'm really excited to introduce this research because this is the first demonstration of the steering of directional thermal emission. So nobody demonstrated the steering of directional thermal emission until now. And this is the collaboration work with Wisconsin Medicine and the Northrop Grumman. I really appreciate them with this great collaboration work. So I introduced some of the background and the motivation of this work. As a start point, I briefly talk about the mid-infrared optics. The mid-infrared is a part of the infrared with wavelength range 2.5 to 25 micrometer, where actually this wavelength range is different depending on the document, but yeah. So there are several important characteristics of the mid-infrared. One is the atmospheric window, that is a transparent sky, which could be applied to the wireless communication. And it has the molecular fingerprint. This is really important as a sensing application. And the other is the daily lab thermal emission. That is the thermal emission from room temperature to a few hundred degrees of Celsius. So here I focus on this thermal emission. Okay, let's briefly talk about the thermal emission. The thermal emission is the electromagnetic radiation from the charged particle in general for atom, molecular lattice, and so on. The radiation pattern of the thermal emission is isotropic, so there is no directionality. Also, it has very broad spectrum range from UV to infrared. As this phenomenon happens everywhere if there is some finite temperature and it has a broad spectrum range, this phenomenon has been used in many applications like the explaining temperature, Doppler shift, and so on. The reason why I focused on mid-infrared thermal emission is related to the mid-infrared light source. So in the mid-infrared, yes, there are various of the light source exist, but mainly two types of the light source has been mentioned. So the one is the thermal emitter and the other is the quantum cascade laser. In the case of the thermal emitter, they are very good because it is cheap and it has wide operation ranges. But the problem is it has poor coherency and the beam quality, so it is difficult to use for the application that requires a good quality light source. On the other hand, the quantum cascade laser has a very excellent property of the coherency and beam quality. But the problem is, it is in general very expensive due to the complexity of the fabrication and its operation ranges is limited. So here my question. If we increase the beam quality and the coherency of the thermal emitter, is it possible to replace the quantum cascade laser? Yeah, so I tried to do this. So as a start point, I will briefly talk about development of the thermal emitter. So in early stage, people try to make some thermal emitter by mechanical engineer the bulky structure. In general, actually, this follows the general thermal emission property like omnidirectional broadband. But as advent of the metasurface, people can control the surface emissivity by using some nano or micro structure, and here they can demonstrate that directional or frequency selective emissivity spectrum could be achieved. As a further step, if we include some kind of the active material in the structure, then actually we can change emissivity spectrum by applying the voltage, temperature, and so on. Then my question is, what is the next step? So until now, people shows that the emissivity frequency spectrum could be modulated by applying external voltage, external signal. But nobody shows that whether it is possible to steering directional summer emission. So I think this is my next challenge for this area. So to achieve the emissivity modulation, actually there are many different scheme has been proposed. So phase changing material, photodoping, and so on. But in our case, we think other material as the graphene. Graphene already has been applied to this area to realize such as the high-speed blackbody emitter or emissivity frequency spectrum modulation. So I think graphene is a really promising candidate to achieve our goals. And the other good reason to select graphene is our group already has been shown many mid-infrared active devices by using the graphene. So yeah, I think the graphene is the best platform to achieve this goal. So this is the objective of our research. The steering of directional summer emission by using the graphene, electrically tunable graphene metasurface and some delocalized mode photonic resonator. I will talk about why delocalized mode is required. So now I talk about some operation mechanism of how to achieve the directional summer emission and how to realize the steering of such a directional summer emission. So I introduced important concept, the spatial coherence. So the concept of spatial coherence is quite simple, but not familiar. So when there is some light source, and you select 2 points in the light source, and each point will emit the light, right? So like this one. And the wavefront of this each emitted light will be propagated like this one. And when we measure the overlap point, like this red dot, then actually, depending coherency, we achieve different results. So for example, sometimes we can achieve like this result. In this case, actually, the phase relationship between two light sources is fixed. So actually, we can obtain such something like the sinusoidal shape amplitude variation. So this kind of the fixed phase relationship between two light sources is the spatial coherent. On the other hand, sometimes we can achieve this highly fluctuated amplitude spectrum. In this case, actually, there is no relationship between two phase points, and this is called as a spatially incoherent. Why this is important? So let's think about some array of some radiator. And if the pace of each radiator satisfies this linear shape, so what it means that there is some afferent phase relationship between radiator, then we can achieve such a directional summer emission by using some destructive or constructive interference. On the other hand, if the phase relationship isn't exist, so there is some random fluctuation, actually we cannot achieve this directional summer emission. And some interesting point in this area is that if we design some delocalized mode resonator, then actually this summer emitter actually follows such a behavior of the delocalized mode, so we can achieve very good spatial coherence. The next important concept is the spatial distribution. Let's assume that the field is confined in small resonator like this red area. So if we press transform this field distribution, actually we will obtain such a broad spectrum because the mode is spatially localized. In this case, as it includes the many of the wave vector component, we will obtain such an absorption spectrum that is angle independent, so isotropic. But if we use some delocalized mode that is spatially distributed, then if we transform this one, we can achieve this Schwinger peak. And in this case, actually, absorption spectrum is highly depends on the instance angle. So this result shows that we have to avoid some localized mode because this is the angle independence, so this plays a role of some background absorption. So by using this concept, firstly, I designed the localized model resonator. As I mentioned, to achieve the spatial coherence, a high spatial coherence, we have to use the localized mode. So we have to prepare this resonator, and in my case, I prepare the vertically oscillating fabric resonator like this one. And this has excellent wave vector selectivity. And next one is non-resonant metasurface. So here we use the graphene, so it is actively tunable, but to avoid some localized mode to eliminate some background absorption, we use some non-resonant metasurface. So by combining this, we proposed this structure, and this shows that depending on the graphene status, actually we can steering the emission direction. I will I will I will talk in detail next slide. So let's imagine this simple Fabricated resonator. So the mode is confined by two meters. One is the fixed and the other is tunable meter. And the mode resonance condition and oscillation direction is determined by Fabricated condition like this below equation. So let's assume that we change the phase of reflection phase of tunable meter. Then to satisfy this relationship, actually the propagation phase, that is the oscillation direction, should be changed, right? And we further change and direction is also changed one more time. And so it means that if we change the reflection phase of this tunable meter, that corresponds to the metasurface, actually we can change the oscillation direction, right? So then why this is related to the emission angle? So if we think about the oscillation angle and emission angle, then actually it follows the Snell's law. So it means that if we increase the oscillation angle, the angle also should be changed to satisfy this emission angle. So this means that actually oscillation angle modulation is equivalent to the modulation of the emission angle. So based on this, we shows that we realize this tunable meter by using the graphene metasurface, and as some given graphene status, actually reflection phase is top 1 and the oscillation direction and emission direction is given like that. And if we change reflection phase, then as I said, now we modulate the oscillation direction, and following this, the emission direction is also changed. So this is the principle of the directional thermal emission steering. So next, I talk about some design of this metasurface and structure, and also the experimental demonstration of our work. As a start point, I briefly talk about some detail of our metasurface. So as I said, we need some tunable meter, right? And in this case, people will think that then maybe the graphene could be lower of the reflector. So how about just to put the graphene as a reflector? Well, this make the fabrication make very simple, but the problem is simple graphene layer has too weak confinement. So interaction with the reflected light is very weak, so low modulation efficiency, and as the refraction coefficient is very low, we cannot support the fabricated mode. Regarding this, in our previous work, when we combine this graphene structure with some plasmonic structure, then actually the impedance match by this plasmonic structure can significantly improve the electric field at the graphene. And also, this plasmonic structure plays the role of the reflector. And thus, we propose this type of the metasurface that combine the graphene and also some nanogap plasmonic structure. By using this one, actually, we can increase the interaction with graphene and the Fabricated resonant mode, so improve the modulation efficiency, and also thanks for this metal structure, we can well confine the Fabricated resonance mode. So to understand the dynamic behavior, our proposed structure, we construct the very simple but powerful model like this one. So this is similar to the coupled mode theory, and here the metasurface is assumed to be very simple thin film structure. And here the total absorption is actually given like this one. So in conclusion, the total absorption is determined by the interference of this direct reflection from the metasurface and the Fabry-Faro transmission term. And if our model is correct, actually this Fabry-Faro term could be described by this simple equation. So if we plot the amplitude and phase of direct and Fabry-Faro refraction, as you can see that, so as I said in first, we have to design non-resonant graphene metasurface to avoid some background absorption, right? So here you can see that the direct refraction of the metasurface has no any resonant behavior. On the other hand, the Fabry-Faro resonance shows some kind of resonance behavior. Here, please focus on this black dotted line. You can see that at this peak of this Fabry-Faro transmission, actually they show kind of the destructive interference. It means that the Fabry-Faro resonance frequency is the same as the maximum absorption, and that actually determines some emission angle. So to obtain this coefficient, actually we have to calculate the metasurface simulation like below structure. So if we calculate this, we can obtain some transmission coefficient and reflection coefficient, and their amplitude and phase depends on the Fermi level. But please focus on this one. So this is the amplitude and phase modulation of the reflection coefficient. And as I said before, if we change reflection phase of the tunable meter, we can change oscillation angle, and follow this, we also change the emission angle, right? And this graph shows that if we change the graphene status, actually we can modulate the emission angle. So this is the calculation result of the total absorption and the phase difference. And you can see that, as I mentioned in priorly, so the absorption is maximized when the destructive interference happen, right? So if you can see that actually the total absorption is maximized when the phase difference becomes pi, that is destructive interference. And we can compare our model result at actual full wave simulation based on FEM, and it shows a great match. Also, we calculate for different instance angle, and it also shows very well. It means that our proposed simple model exactly capture the dynamic behavior of the devices. Next, we calculate some phase map and emissivity map for different angle and Fermi level. Here, you can see that the maximum absorption angle, that is the emission angle, is gradually changed if we modulate the graphene status, that is the Fermi level. We also calculate the non-local response, that our calculation is really well describe our structure. So in our structure, actually the gap size is 14 nanometer. So there is a report that when the graphene width becomes a 14 nanometer or something like a sub 100 nanometer, actually their response cannot be described by the simple classical electrodynamics, because there occurs some kind of non-local effect. So here, as our gap is 14 nanometer, we concern that this thing happen. So the below image is the electric field distribution, and we calculate the non-local response for each case. So what I mean is that considering the non-local effect in the metal structure or graphene or combine these two. And thankfully, our structure is almost free of the non-local response. That's because, as I said, actually the sub 100 nanometer graphene structure affected by this non-local response. But as you can see this image that electric field is spatially dispersed because there is a gap between plasmonic structure and graphene. So this is why this makes the effective graphene width as much wider than gap, so we can avoid such a non-local response based on performance degradation. So now I talk about the experimental part, and this is the fabrication process. Firstly, we deposit the gold and chrome on the backside of thick oxide, which plays a role of the backgate. And then we transfer graphene on the thick oxide layer. Then we deposit the hafnium oxide as a passivation layer for the HSQ patterning. And we make some sub 100 nanometer gap by using the HSQ. And then we deposit the gold to make some plasmonic structure. Actually, there are many issues in the fabrication process, but I think one of the most important thing was this leakage current issue. As you know, since we realize a tunable meter by using the graphene, we have to apply the voltage between the bottom backgate gold refractor and our metasurface. Here, as we use the very resonator, we require almost a few micrometer scale thick oxide layer, and this oxide layer should have low leakage current for high voltage apply. So to make this oxide layer, actually firstly we try to deposit the PCVD oxide layer because PCVD is very good equipment to deposit thick oxide layer. But the problem is actually the oxide quality is not so good. So there was a serious leakage issue. So to solve this problem, actually we try to use membrane. So this membrane is created by the LPCVD process. So it is better quality than PCVD oxide. Where actually we also try to create such a large area membrane that is millimeter scale, but it was not easy. So in actual fabrication, we use such a the commercial product provided by the Norcada. They provide really good, excellent membrane. So based on this fabrication process, we make like these devices where it looks quite complex, but as I say, this is simply fabricated resonator with the graphene metasurface. The light image is our SEM and the OM image as the gold is covered, so we cannot find any pattern in the OM. And to measure the emissivity of the structure, we attach our sample to heating stage, and also we collect the emitted power by using the pre-transform interferometer that is the built-in component in the commercial FTIR product. Also, to measure the angle-dependent response, we use the rotation stages. By using this measurement equipment, we firstly measure the emissivity frequency spectrum like this. So left is experiment and right is theoretical calculation. They show quite good match, and the one of the good thing that I think was actually the measured emissivity is higher than 0.9. This is because if we want to use this as a practical device, emissivity should be high. And in view of this high emissivity is a very good sign for practical application. And next, we measure the emissivity angular spectra. And actually, the experimentally observed steering angle was at 16 degrees, but theory is slightly higher than this, where there could be some similar reason why this thing happened, but nevertheless, what I want to emphasize is that we achieve the steering of the directional thermal emission. As a further step, not only the angular spectrum for fixed frequency, we also measure the angular spectrum for various frequency ranges. And if you compare the theory and experiment, although there was a slightly difference in the angle, but it is really well matched. In addition, where in this time we just show only for in the range of the 30 degree, but if we can apply more voltage and more higher Fermi level modulation, actually we can achieve larger than 60 or even 80 degrees could be achieved. So now I talk about some conclusion. As I mentioned earlier, our objective is the steering of directional thermal emission by using the Nonlocal model resonator and the graphene metasurface. Now I think you guys understand why these two components are required. So here I showed the design of the delocalized photon resonator for directional thermal emission, and also the design of non-resonant graphene metasurface. And most important thing is, this work shows the first demonstration of electrical tunable thermal emission steerer. I think this is the kind of the foundation for not only scientific field but also industry. In the case of scientific field, it provides a very strong connection between incoherent light and coherent light technology such as the LiDAR, photonic integrated circuit, and so on. In the case of industry, actually this could be applicable for military infrared beaming, satellite radiated cooling, wireless communication, and so on. As I mentioned earlier, that this is the collaboration work with various groups. So in KAIST, Professor Min-Seok Jang and me participate in this work. And it's in the Wisconsin Medicine, the Professor Victor Brott, Dr. Joel, Professor Michael Katz, Margaret, Dr. Cheng Hao. And in Northrop Grumman, the Philphone and Luke was participated. I'm really appreciate for my collaborator for this great job. So yeah, this is end of this video. And if you have any question, please contact my email for the question. Thank you.